This is our last lesson in Unit 9. We're going to explore area and arc length in polar coordinates. And as we continue our investigation in polar curves, we're going to look at finding areas in rectangular coordinates. Remember, we used rectangles to approximate the region, but now in polar coordinates, we'll use sectors of circles. It's just another small change will be in our language. So in rectangular equations, we found the area under the curve. But with polar equations, we will find area enclosed by the region of a polar curve. So just keep that in mind as we go along. Here in this first graphic, we want to look at the area of a sector. So if you think about the circle, we have this sector here, where we have the radius and we have the angle theta. So the sector area is going to be pi r squared, so that's the area of the circle, times the fraction of the circle that's shaded. So that would be theta over 2 pi. And if I color this in here, we're thinking about this as the fraction of the area that's shaded. Whoop. So if you think about the area sector as the area of the circle times the fraction of the circle shaded, we get 1/2 theta r squared. And in the larger picture here, if this represents our angle alpha right here, and this represents our angle beta right here, then this is the region we're thinking about. So you're thinking about imagining a very small slice of this, where the d theta is very small, and your radius is modeled by the function f of theta. So the formula we'll use, if f is a continuous and non-negative on the interval, on the closed interval from a to b, then the area of the region bounded by the graph of r equals f theta between two radial lines, one theta equals alpha and the other theta equals beta. That's given by the area formula is 1/2 of the definite integral from alpha to beta of f theta squared d theta. And that's our 1/2 r theta squared d theta. So in example 1, we'll find the area inside of our cardioid. R is 1 plus cosine theta. And one thing we know is that the angle theta is going to be somewhere between 0 and 2 pi in order for us to go all the way around a full revolution. So the area is 1/2 from 0 to 2 pi of our r theta, that's 1 plus cosine theta, quantity squared d theta. Expanding this in the middle, we'll have 1/2 from 0 to 2 pi, and that would give us 1 plus 2 cosine theta plus cosine squared theta d theta. And then using some of our trig identities, from 0 to 2 pi, we have 1 plus 2 cosine theta, and then cosine squared, we can use the formula 1 plus cosine of a double angle divided by 2 to be able to reduce that cosine squared. And then integrating, we have 1/2 of theta plus 2 sine theta, and then the integral of 1/2 is theta over 2, and the integral of cosine 2 theta divided by 2 is going to be negative sine of 2 theta with the chain rule, so we're dividing by 4, evaluated from 0 to 2 pi. And then using our A and B values for the fundamental theorem, we've got 2 pi plus 2 sine of 2 pi, which this goes to 0, plus 2 pi over 2, minus the sine of 4 pi divided by 4, and again this goes to 0, and then minus, so we got this first part for 2 pi, and then minus 0 plus 0 plus 0, and then the sine of no, this one is 0, sine of 0. So all of those are 0. And then substituting that, we've got 3 pi over 2, I believe. So 2 pi plus another pi, 3 pi divided by 2. So our area is 3 pi over 2, given this entire area here shaded inside that. So this entire area is 3 pi over 2, using our formula for area of a sector, area of a polar curve. Example 2, we want to find the area of just one petal on the 3 petals r 4 sine 3 theta. So we're going to look at just one petal. So we know that the pole is r equals 0, and that this happens on 0 to pi. So we're thinking about 4 sine 3 theta equals 0 when sine of 3 theta is 0. So 3 theta is 0 at 0, and 3 theta is 0, happens at pi. So theta is pi over 3. So we're looking at the angles from 0 to pi over 3. In my picture down here, this is our theta equals 0, and this is our angle pi over 3. So we're going to calculate this area, shaded area of that one petal inside here. Now setting up our formula, we have area is 1/2 from 0 to pi over 3 for 4 sine 3 theta quantity squared d theta. So we have 1/2 from 0 to pi over 3, and then expanding this we have 16 sine squared 3 theta d theta. So again, we want to use those trig identities. We know that sine squared of u is 1 minus cosine 2u divided by 2. So if we use this formula here, we can rewrite this sine squared of 3 theta. So that would look like, let's see, take this 16 with this half, so we have 8 from 0 to pi over 3, and we have 1 minus cosine of 2u, and our u is 3 theta over 2 d theta. So if we pull this 2 out here with the 8, we would have 4 on the outside with the definite integral from 0 to 3, and that would be 1 minus the cosine of 6 theta d theta. And then integrating, we have 4 times the quantity theta minus, let's see, we got, minus 1/6 of sine of 6 theta from 0 to pi over 3. So we got 4 pi over 3 minus 1/6 of sine of 6 times pi divided by 3. That's 2 pi. So that's going to go to 0. And then it's minus 4 times 0 minus 0. So all of that is gone. And our area for one petal is going to be 4 pi over 3 for that one petal on the 3-petal cardioid or rose curve. And this is a lemniscate. So find the area inside of one loop. So our radius is going to be the square root of 9 cosine 2 theta. And we're looking for where 9 cosine 2 theta is 0. And that would happen when cosine of the double angle is 0. So that happens. Cosine is 0 at pi over 2 and also at negative pi over 2. So we would have theta could either be pi over 4 or negative pi over 4. And looking at our picture, you can see this is the pi over 4 angle and this is the negative pi over 4 angle. So our integrand would look like area is 1/2 from negative pi over 4 to positive pi over 4. And we have our R value, 9 cosine 2 theta quantity squared d theta. So substituting our values in for pi over 4 and negative pi over 4, we have, pulling out the 4 here, we have 9 over 4, and this is going to be 1 minus negative 1. So that's 2 times 9 divided by 4, and our area under the lemniscate petal would be 9 over 2. Here in example 4, if we want to find the area of the inner loop for the graph of this lemison with the inner loop, we want to recall where the auxiliary graph makes the inner loop. That's where the negative R values are. And solving algebraically, I find that 2 minus 4 cosine theta is 0, either at pi over 3 or 5 pi over 3. So if you consider the auxiliary graph, we would have pi over 3 being the first place, and then that inner loop is going to be created and come back out at negative pi over 3 if we go backwards, or having 5 pi over 3 be the first place and then moving forward in a counterclockwise, we would end up here at 7 pi over 3. So I'm going to choose to use negative pi over 3 to positive pi over 3. And 2 minus 4 cosine theta quantity squared d theta. In this case, I'm going to use my calculator and estimate that value with the definite integral. And I find that the area of that inner loop is about 2.174. So that one I use the calculator for. Moving on with example 5, in this case, we want to find the area of the region that lies, excuse me, inside of the circle, so that's this piece here, and outside of the cardioid, so this is the cardioid here. So shading that region, we're looking for this particular area. Now, if you think about it, we're going to want to find the intersection of those two areas. So we might want to make a note of that. We need the intersection of where those two shapes cross. So we want to think about where is 3 sine of theta equal to 1 plus sine of theta. So collecting like terms, we have 2 sine of theta equals 1. So sine of theta would be 1/2, and sine of theta is 1/2 at pi over 6, and at 5 pi over 6. Now, if you look at the graph, you can see that this one is our pi over 6, and this one is our 5 pi over 6. So to find that intersection, that shaded region R, we're thinking about 1/2 from pi over 6 to 5 pi over 6, and we want to take the circle, the 3 sine theta quantity squared, and subtract out the other piece of the cardioid, 1 plus sine theta squared d theta. Now we can calculate this as, so calculating that on our calculator, it looks like the total area is pi. So just using our calculator to work efficiently here. Let's see, example 6, we want to find the area of the region that this time lies inside of the circle, but lies outside of the convex lemniscate. So shading that particular piece, we're looking for this part here. And then again, modeling that we're looking for those intersection points. We need where 3 sine theta intersects 2 minus sine theta. So where 4 sine theta equals 2, or where sine theta is 1/2, again, we're at pi over 6 and 5 pi over 6. And if you pay attention to the graph itself, you can see there's the pi over 6 intersection, and here's our 5 pi over 6 intersection. So thinking about that, we want the area is going to be the outer part minus the inner part. And then again, putting that together, and depending on our calculator for the calculations, we're looking at the integral from pi over 6 to 5 pi over 6. And we want the outer portion, which is 3 sine theta quantity squared, minus the inner portion, which is 2 minus sine theta quantity squared d theta. And then jumping over to the calculator, I believe you're going to find the area is 5.196. Let's give that a shot. And you can tell the exact answer is 3 times the square root of 3, and the decimal answer 5.196. So depending on which graphing utility you use, your calculator may go straight to the decimal approximation. If you have the CAS version of the Inspire, you're going to get the exact answer. Here in example 7, this will be our last area question. Find the common area for the 4 sine theta and r equals 2. Using our highlighter here, the common area would be this area between the circle and the circle. So I'm thinking about it this way. I have the area of the bottom circle, and I'm going to subtract the outer minus the inner in order to get the exact area that we're looking for. Let's write that down. So I've got the area here, and if I think of the bottom circle, this entire thing, we can calculate that entire area and then subtract out the outer circle minus the inner circle. So the outer circle minus the inner circle to get rid of that. Again, I need the intersection points for where 4 sine theta equals 2, or where sine of theta is 1/2. Again, you see those intersection points being pi over 6 and 5 pi over 6. So there's that first one, and there's the second one. In this case, we're having the entire outer circle. So that's the r equals 2. That's this one. That's going to go from 0 to 2 pi. So that's going to be 2 squared d theta. So that's r equals 2 is this one, the bottom circle. And then we're going to subtract out the pi over 6 to 5 pi over 6. Uh-oh, switched to the wrong tool there. So pi over 6 to 5 pi over 6. So this top one, 4 sine theta squared minus the bottom one, the overlap, 2 squared d theta. And again, I'm going to use the calculator to calculate that entire portion for us. And again, if you have the Inspire, you're going to get 8 pi over 3 minus 2 square roots of 3 for an exact answer. And if you have another graphing utility, you're going to get about 4.9134 for your approximate answer. So it just depends on which calculator you use, what type of approximation or exact answer you get. And then our last two examples, we're looking at arc length of a polar curve. And using the arc length formula, you can see 3 different ways we can write these formulas. So using the formula to find the arc length of the cardioid, the arc length is that entire length all the way around. That length is going to go from 0 to 2 pi, and again, this is a calculator question. So the formula says we can take the r, which is 2 minus 2 cosine. We can square that, and then the dr, d theta, and we can square that and take that integral with respect to theta. So we're looking at from 0 to 2 pi for 1 revolution, and then 2 minus 2 cosine theta, quantity squared, and then the derivative would be positive 2 sine theta, and we're squaring that. That entire term is under the radical. That's the biggest mistake that people make, is forgetting that radical. And then to make it simpler, let's see what we got here. We can take 4 sine squared theta plus 4 cosine squared theta minus 8 cosine theta plus 4 under the radical d theta. So this is 4 sine squared theta. This is 4 cosine squared theta. 4 and 4 is 8, and then plus 4. So 4 sine squared theta and 4 cosine squared theta, that's 4. So we have 4 and 4. That would be 8 minus 8 cosine theta. And then jumping over to our calculator, let's see what we got. And that looks like our arc length is 16. So that was pretty easy. Then our last example, we want to find the length of the polar curve r for negative pi over 2 to pi over 2. So we need to know what the derivative is in terms of theta. So that would be 1/2 times 1 plus cosine 2 theta to the negative 1/2 with the chain rule. So that's negative sine 2 theta with another chain rule of 2. So we can get rid of the 2 and the 1/2 and integrate from negative pi over 2 to pi over 2, the square root, and this is a square root, so we've got 1 plus cosine 2 theta, that amount squared, plus negative sine of 2 theta over this square root of 1 plus cosine 2 theta squared d theta. Let's see, so this is our r squared, and this is our dr d theta squared. And again, going to the calculator to get our result. And again, if you have the Inspire CAS version, our exact value is pi times the square root of 2. And if you have any other form of a calculator that does decimal approximations, your arc length is 4.4428. So we have either pi times the square root of 2, pi square root of 2, or 4.4428. And that, my friends, is the end of Unit 9.